Hello there, professors. I'm Erdem Kocakuşaklı from Ankara University in Turkey. Our presentation name is New Examples of Translating Solitons on a Parallel Light-like Direction in Minkowski 3 Space. This presentation joint work with Miguel Ortega from University of Granada in Spain. I appreciate to him, thank you so much, and thank you so much to organizing committee to organize this workshop. This talk based on our paper with Miguel Ortega. It published in Differential Geometry and its Applications in 2021. Basically, hypersurface called translating solitons if its mean curvature vector equal to orthogonal projection on the normal bundle of K. Here, K is a unit vector field. Now we can give these definitions. Let K be a parallel light-like vector in Minkowski 3 space. An undegenerate immersion PC is called translating soliton on the light-like direction K if its mean curvature vector H equal to orthogonal projection on the normal bundle of K. In this work, we use the standard flat metric in Minkowski 3 space is given as minus 2 times dx dy plus dz squared. Here, x and y are light-like feature-pointed vectors and satisfying the normalizing condition, the inner product of x and y equal to minus 1. This talk contains two main parts. In the first part, we study on graphical surface. We examine the translating solitons of the mean curvature flow for graphical surface, which are translation surface. And then in theorem 1, we classify our solutions, and then we examine the completeness and entireness cases in our corollaries. In the second part of the talk, by using one-dimensional subgroups of parabolic isometries of three-dimensional Minkowski space whose axis is light-like, we study surfaces obtained by letting this subgroup of isometries act on a suitable profile curve. And then we classify, in theorem 3, we classify those translating solitons which are invariant by this subgroup of isometries. Let M be a smooth manifold and let Ft be a family of smooth immersions in a semi-Riemannian manifold with the mean curvature vector Ht. F0 is called a solution to the mean curvature flow if the following equation true holds, and then F satisfies the conditions its mean curvature vector equal to orthogonal projection on the normal bundle of K, then it's possible to define the forever flow PC. PC in here, PC equal to F plus T times K. And clearly, the expression 3 holds. Now, let's consider PC is a graphical surface is given in expression 4, and then we can easily calculate the partial derivatives of PC and the coefficients of the first fundamental form are given in expression 5 and 6. And we can easily obtain the unit normal vector, and the coefficients of the second fundamental form are given in the expression 7 and 8. Then we can compute the mean curvature function is given in 9, and by using the definitions of translating soliton on the light-like direction K, we obtain the partial differential equation is given in equality 10. Now, let's consider PC is a translation surface. Then our partial differential equation turns into the following equation is given in 11. Now, we have two cases. In the case 1, if the second derivative of a equal to 0, then our equation 11 turns to the equation 12. And then if we change the variable, phi equal to b prime, then we have the equation 13. And case 1.1, if e1 bigger than 0, then we have the solution u is given in expression 15. In the case 1.2, if e1 less than 0, after some computations, we have these solutions are given in expression 19 and 20. In the case 2, if the second derivative of a different from the 0, then again we have two cases. In the case 2.1, if we differentiate the equation 11 with respect to y, after some computations, we have the solution u is given in expression 25. In the case 2.2, with the previous idea, we differentiate the equation 11 with respect to z. Then we have the equation 26. And then in the case 2.2.1, if we consider the third differentiation of b equal to 0, then again we have the solution is given in 25. In the case 2.2.2, after some computations, we have the solution is given in case 1. Then now we can give our theorem. Let's consider the three-dimensional Minkowski space with the usual metric written as G, and PC be a translation surface. If PC is a translating soliton on the parallel light-like direction K, then U is one of the following. These solutions are called type 1, type 2, type 3, and type 4, respectively. All examples in theorem 1 are flat because their Gauss curvature equal to 0 in all cases. And now we can give some corollary about the completeness and entireness of our solutions. If we consider the solutions type 1 is space-like, entire, and complete, the solutions of type 3 are time-like, never entire, and incomplete. Solutions of type 4 is time-like, not entire, and not complete. Our solutions of type 2 is space-like when E1 bigger than 0 and time-like when E1 less than 0. Moreover, any inextensible solution C is entire but not complete. Now we summarize these corollaries in the following table like this. Then plenty of mean curvature flows in the Minkowski two-plane are computed by Heldersons. In particular, the translating solitons are curves cosinus hyperbolic x equal to exponential y minus t, sinus hyperbolic y equal to exponential t minus x, and x plus y equal to exponential x minus y plus t, which travel in a space-like, time-like, and light-like direction, respectively. These curves can be seen as the corresponding Grim Reaper curves in two-dimensional Minkowski space. If we consider the projection pi, the preimage by pi of each curve provides a translating soliton in the space-like, time-like, and light-like direction, respectively. This can be seen as the corresponding Grim Reaper surfaces in three-dimensional Minkowski space. The natural transformation is x plus y, x minus y goes to 2u to v to obtain our coordinates. Then, if we take E1 equal 2, B1 equals 0 in case 2 in theorem 1, we obtain the corresponding Grim Reaper surface in the light-like direction by written our way. Now, let's consider the following subgroup of direct time orientation preserving isometries is given in the expression 29. And let's consider the usual matrix multiplication. And for the next theorem, we need the following region is given in expression 30 and 31. Now, let's give this theorem. This theorem is given by Baros, Caballero, and Miguel Ortega in their paper. Theorem said to us, let M be a connected surface and phi a non-degenerate immersion. Then it's A3 invariant if and only if one of the following statement holds. In the Riemannian case, there exists a regular space-like curve alpha. By using the A3, we can construct our surface. In the Lorentzian case, there exists a regular time-like curve alpha. By using the A3, we can construct our surface. Now, let's consider the regular curve in S alpha, and by using the A3, we can construct the A3 invariant surface PC is given in expression 32. And we can easily compute unit normal vector, and we can obtain mean curvature function is given in the equality 35. Next, by using the definition, we have the equality 36. And then we can obtain the ordinary differential equation is given in the equality 37. And let's assume to y equals to s, and we examine the x. Then our equation transforms into the equation 38. With the standard computations, our ordinary differential equations turns we obtain the solutions to this ordinary differential equations is given in the 39. It's space-like when E0 less than 0 and PC is a space like when E0 bigger than 0 and time like when E0 less than 0. Now let's assume X equal to S and let's examine the Y. Then our ordinary differential equations transforms into the equation 14 and then we have the equation 41 and by using the phi we have the solution we obtained y is given in the equality 43 and then we can give our theorem. The theorem said to us let PC is a A3 invariant surface such that it's translating soliton on the parallel light-like direction K. Then the profile curve alpha is one of the following. And now we can give our references. Thank you very much for your kind attention.